Hello everyone, in this tutorial I'm going to show you how to simulate a simply supported beam in Abaqus, and we're going to compare our finding in software with a hand calculation. Okay, so first of all, let's look at the example that we have here. So we have a very simple beam with a length of 5000 millimeter, and they have a pin load in the middle, which is 6000 Newton. On one side is a pin, on the other side we have a roller, and the cross section area, as you can see, the top flange width is 80 millimeter, and the depth of a section is 200 millimeter, and the web thickness is 10 millimeter, and the top and bottom flange thickness is 15 millimeter. We're going to use the steel material. Young modulus is 200 gigapascal, Poisson ratio 0.3, and the yield stress is 250 megapascal. So before starting example, I want to show you a hand calculation of the to find the bending force, maximum bending force and moment, and also maximum displacement in this beam. So basically, the first thing we need to do, we have to find the second moment of inertia, and the formula basically depends on the geometry that you have, but for a rectangle the formula is 1/12 b times h, which is a height, cube. In this case, so the I-beam shape, as you can see, is not a rectangle by itself, but it's a combination of rectangles. So what you can do, you can have three separate rectangles and find the moment of inertia. But the problem is that in that case, then your the eye is not going to be in the middle. The best thing to do is to have the geometry in a symmetric way, is that to consider one big rectangle and subtract these two small rectangles from the big rectangle that you have in order to find the I value. Okay, this is basically what you normally learn in the first year of engineering course at university, so I'm sure that you should be familiar with the second moment of inertia. So what I have done, so it's 1/12 times 80, which is the width, times 200 height, minus 1/12, and here, instead of using 35, I combined this together, so I had this one 70 times 170 cube, and that would give me 24.68 times 10 power 6. So that's basically is my second moment of inertia. And then we have the formula for maximum deformation, that is displacement equals to force times length of the beam divided by 48 times Young modulus and times second moment of inertia. So now if I put the values inside that formula, so the force is 6000, the length of the beam is 5000 millimeter, and 48, we said that we're going to use a steel, so 2 times 10 power 5 and times 24.68 times 10 power 6 that we found from the previous formula. As you can see here, I'm keeping all the unit in millimeter, so the force is in Newton, obviously the length is in millimeter at the top, and the Young modulus here, as you can see, is megapascal, and we have millimeter here, and as you can see, the moment of inertia here is millimeter as well. So the displacement that we found here equals to 3.16 millimeter. Next step is to find the bending moment for simply supported beam with a point load, and then we have M equals to PL divided by 4. That's a formula for it, so it's equals to 6000 times the length of the beam divided by 4, so that's 7.5 times 10 power 6 Newton millimeter. And bending stress formula comes from M times Y, which is the neutral distance, divided by I, which is a moment of inertia, and because this is a symmetric, obviously that's in the middle, and that equals to 30.38. Okay, so we have these values. Now we want to do exactly the same thing in a software, see that if we're going to get the same result. So I'm going to minimize this one and start a new model, and I'll just call this one simply beam, and I'll start with the part. So either I can create a part from here or here. So click on create part, and at the top type beam, I'm going to keep it 3D wire, and I'll make it planar. Click on, before clicking on continue, we need to take care of this approximate size. As I mentioned that the length of the beam is 5000, and I'll just make this one 5000 and click on continue. You can keep that at 200. It's not really going to change your sketch. You're going to just have a smaller area of for this sketch, which is not going to really affect the result. If your sketch is here, that's not going to affect your sketch, and it's not wrong. This is just to help you for sketching basically. So I'm going to create a line, and I know that from this corner to this corner should be 5000, and I can also draw give a dimension to this, and as you can see this is 5000. Cancel this one, click on OK. So I've created this simple line that is going to be my beam. Next step is to create a material properties. So go to property and create a material. So that's going to be steel, and for mechanical I'm going to use elasticity, and that's going to be 2E5, and that basically represents 2 times 10 power 5, as we had in the material property section is 200 gigapascal, or in megapascal is 2 times 10 power 5. So you have to be careful of your units, as I mentioned in the previous videos, that we don't have a unit system in Abaqus, and you have to take care of the unit system. And because I draw my geometry in millimeters, so here I should have it as SI millimeter, which is megapascal, and Poisson ratio 0.3. Also we can add plasticity data here as well. So I have this data here, so I'm gonna import this to here. So that's 250 and 0, and this is 264 0.024, and this is 49 316 0.074 326 0.099. Okay, this is, I think this is enough, so you don't need to do all of them. So I've added a yield stress and a plastic strain. So now click on OK. Next step is to create a section for this beam. So I'm going to go to create profile and select the I beam, click on continue. Now I have to give a dimension of the flank and the web. So the first one is the middle of this beam, because it's symmetrical, so obviously it's going to be in the middle, and that's going to be 100. The height is 200. B1 is a flange, so that's going to be 80, and the same thing for the bottom one. Thickness of the flange is 15, and same thing here, 15, and this one is 10 millimeter for the middle one. Click on OK, and then create a section and select on beam section, and click on continue. And from here, as you can see, we have one profile, one material, so click on OK, and then assign that to a section, click on done. And as you can see, we have one section here, click on OK. So I'm done with this one. Then I have to assign a beam direction, so select the beam section orientation, select this line, click on OK, and click on OK. And as you can see, this is tangent, and number 1 and number 2 are normals. Then click on OK. And to check if you have done everything correctly, go to part display option, and from here activate a render beam and apply this one. And if you rotate your model with the middle of the mouse middle button, you would be able to see the I-beam that we just created. Okay, so now next step is to go to assembly and import a file, import your model. We have only one model, and I'll keep it as a dependent. Click on OK, and then in a step I'm going to create a step general. We can keep the non-linear on because we gave the plastic deformation. For increment, this is going to be a quick simulation. We don't really need that many numbers, but just for a practice, increase this number. We generally don't keep this one as 100. I always recommend keep this one as at least 10,000, so the software won't stop due to a lack of increment. But for this example, obviously you don't need that many increments. But however, this is not really going to affect the computational time. It's just a good practice to keep that value always high. So increment size for the initial 0.1, and this for minimum 15, and click on OK. And the next step is to request the output. So if I edit this one, generally Abaqus give us the stress, strain, displacement, and force. However, in order to find the nodal forces in a beam, such as moment and shear forces, we have to activate this one in order to see those values. So nodal forces in beam section orientation. Click on OK and close this one, and then go to interaction. So in interaction we don't have anything because we have only one part, so we don't have to create any contact or coupling. And the next one is a load. Okay, in load, what I'm going to do, I'm going to fix one side, and on the other side I'm going to apply a roller, and in the middle I'm going to apply a load. So let's start with a create boundary condition, and the first one, and select this, the left side, click on OK, and select the pin, which is X, Y, Z are 0, and for the other side select displacement and rotate your part by using a mouse middle bottom, and select this point, click on OK, and here we want to allow this one to roll on the x-axis, but it should be fixed in y and z axis. So u2 and u3 are 0, however it can move to right side, which is the x-axis. So click on OK. Next step, to apply a load in the middle, we have a point load in the middle, and in order to create that specific point there, what we can do, we can go to part. I'm going to just deactivate this render so I can see my model here, and then I can actually divide this line to two lines, so by using a partition edge. So if I select this one, and I can select the point that I want to, so basically it says that select the point that you want to create this partition. However, this is not really accurate because we want it to be exactly in the middle. So what I can do, I can actually give a distance, partition interparameter. So if I select this line, click on done, then actually I can say where I want to put this one, and obviously I want it in the middle, and that's basically 0.5. It means that's exactly in the middle of the your model. This is not really straightforward. The reason is that, for instance, this is normalized, so any length that you have there is 0 to 1, so you have to find the percentage. Imagine if that point was here, I have to find that percentage because the edge length is normalized, so you have to find that percentage to find the location. And so it's not as straightforward. For instance, you have 5,000 millimeter and you can type here 2,500, or imagine if you wanted it at 2,100, you have to find the percentage for 2,100 and you put that percentage here to be able to create a section cut. Okay, so I'm going to create this section cut and click on done. So I have one side here, so I have two. So make sure that you are using a interparameter rather than a specified. This is basically by location. So if I go back to load, then I can create a load, a concentrated force, click on continue, select this one, click on done, and here I'll make this one 0, this one 0, and this one minus 6,000 is in Newton. Click on OK, and again I'm going to go to view and display object, and activate a render. So as you can see, this is exactly what we wanted. So make sure that your cross section is correct in comparison to the load, so it's not in the wrong direction. This is very important, otherwise you're not going to get a correct result. The next step is a mesh. So I'm going to apply a mesh to this one, because obviously I imported this one in dependent, so I have to, in the part section, I have to give a mesh to this one. So I'll select these ones, both of them, click on done, and let's see what is the approximate size. 250 is a little bit too big. I'll make this one, let's say 100. Yeah, this is better, so I'll make it 100, click on OK, and create a mesh part. Yes, so I apply the mesh to the geometry. The last step is to create a job. So if I've done everything correctly, I shouldn't get any error, but we'll see in a second. So I'll create a job and I call this one beam number 2, continue, OK, and I'm going to submit this job, and I can monitor it to see that if I have any error. So as you can see, there wasn't any error here, so we have to wait for simulation, and as I mentioned before, it's going to be a quick one, so it's done after 6 increments. So I can now monitor result, and by going to the form shape, I can see the first thing I want to check is a displacement. So displacement is 3.24, and if you remember, when we calculated our displacement, what we found there is 3.16, so very close, acceptable error range. And as you can see, displacement is very small, so for better visualization you can click on common option, and from here uniform, for instance, change this one to 100, so you can actually see the displacement. This is obviously simply for visualization, and this is not affecting your result. So the magnitude is 3.24, and I can animate this one as well, so how basically the deformation occurs in the beam. And so the next step is to basically check our moment and force. Before doing that, I have to create basically path, because I want to demonstrate those in the path. So let's cancel the video. So creating a path in Abaqus could be a little bit tricky, especially for 2D wire geometries, because in 3D you can actually see the element, you can pick the nodes, but in 2D wire or 3D wire, the elements are not really clear. So especially if you have a complex geometry, it would be difficult to select a node for creating a path. So we do these further steps to make it a little bit easier. So first of all, I'm going to go to view ODB display option. I'm going to deactivate the render beam, apply this one, and then go to option common, and in labels activate the show node labels and show node symbols. Obviously you can change the symbols, but I'm happy with this one, and click on apply. So as you can see, now I can see the nodes number and the location of it. So this makes life much easier when I want to select a node. Obviously the number of the node depends on the mesh section, so the finer mesh you will have more nodes, and obviously the more nodes means that you have more nodes on the path, and when you want to export the data you will have more details on your path. So first let's create a path here. I'm going to select node list, continue, and I'm going to say add before, and select this one, this one, this one, this one, this one, and click on OK. So as you can see here, we have a logic. So we selected the first one, and rest of it is 4 to 7 because the number goes 4, 5, 6, 7. So what I can do, I can look at what is the last number here, and 51, and I can put 51 at the end, and the software will select all the nodes. However, you have to be careful, especially if you have two pieces, or you partition your model like what we have done. If you remember, I partitioned my model, so I have two lines, one line here and one line here, and as you can see in the middle I have a node that the software didn't select it. I jumped through this one. So what I need to do, basically, I need to, instead of 51, I should put 27, and then select the next node, which is number 2, and then comma again at 28, 51. So as you can see now, software selected that node, and I can also select the last one, which is 3. So now I created a line which has all the nodes in it. Click on OK, and in the next step I can actually export the result on this line. So first thing, let's just export this the displacement result. If I go continue, select the path, you can have as many paths as you want, and the path point, I can say include the intersection or all elements, but in this case I don't have to do this one because I've selected all the nodes, which means that I've selected all the elements. And here the distance is true distance, so it's going to be 5000 millimeter, and obviously you can normalize it to become from 0 to 1. But let's plot this one. So as you can see, the displacement is 3.24 as we found, and the maximum is in the middle. So obviously this is the absolute value, and but the displacement here that we had is negative, but what you get here is the absolute value. So the next step is to plot a shear and bending moment. So and that's why we activated these nodal forces in beam section. So you can see that we have number 1 to 6, and these are basically the directions of the forces. And if I want to plot the shear force on a y-axis and apply this one, so as you can see now I have node force number 2, and I can plot this one. So you will see that the shear force basically starts from minus 3000 and it goes up to 3000. And now we can also see bending moment for this beam, and as you can see the result is goes to a little bit over 7. So in order to have the values, the best thing to do is basically to save these values. So what I'm going to do, I'm going to plot this one and save this one. I'm going to call this one moment, and I'll do the same for shear as well. So I'm going to plot the shear and save this one as a shear. So now I can go to plugins, tools, and Excel. Let's do it for moment first. And what I'm going to do, I'm going to just select the line, and I'm going to divide this one by 10 power 6. So we transfer this one to Newton millimeter. So as you can see, the maximum value that we have is minus 7.49, and we can compare this to our hand calculation, which is like 7.5 times 10 power 6 Newton millimeter. Okay, so this is basically the bending moment maximum that we found. And also we can do the same for shear value. So I can go to tools, shear value, and export this one. So we will find this one here. Again, I'm going to go to a line, and as you can see how the result goes from minus 3000 to 3000. Okay, now if you basically use one of these online beam calculator and draw your geometry based on what we had, and you'll see that we got exactly the same shear and bending moment. Obviously the signs are not really important, the values are important, because some of them could be absolute value and some of them could be actual value. Okay, so we have these ones. The last thing to check is the stress value. So the stress value, also we can check it from here, is 27.72, which is a little bit shorter than 30.38 megapascal that we found here. Okay, so this is the end of this tutorial. I hope you enjoyed it. In this tutorial you learned how to basically extract a moment and shear force diagram from Abaqus software, and also compare your result with a hand calculation. Thank you so much for watching, and I hope to see you in the next video. Thank you.